I'm Minho Kim, from Department of Applied Chemistry in Gyeonggi University. And first, I'd like to thank Professor Choro Che for inviting this great conference. And I'd like to talk about the development of Van der Waals correction method for density functional approaches today, especially for material simulations. So before beginning starting my talk, I'd like to talk about my study of interest. So I basically do DFT simulations for energy materials like photocatalyst and electrocatalyst. So I'd like to say I feel very humble and pressured by very difficult theories, but I do very simple DFT simulations, and I developed a very simple DFT correction method that I will introduce today now. So basically, I did much of simulations at the interface of materials, such as catalyst. So doing these simulations, I felt the importance of Van der Waals interaction, which is non-bonded interactions occurring at the interface between the molecules and surfaces. So, and I found it is very well known that DFT does not depict the Van der Waals interaction very well. So I studied the Van der Waals correction methods during my PhD work and still on. So Van der Waals interaction is very ubiquitous interaction occurring in nature from biological systems as well as molecules observed on catalytic surfaces and layered materials formed on substrate surfaces as well as actual energy processes occurring in battery materials. So these Van der Waals interactions not only the organic molecules, but also the interactions between the molecules in metals and layered materials and metals and ionic materials as well. So we need to understand Van der Waals interaction regardless of the dominant types of interactions in these kind of systems to understand the accurate structures and energetics of the chemical processes. So basically, the Van der Waals interactions, especially London dispersion interaction, is the type of Van der Waals interactions. So it is one of the non-bonded interaction which occurs based on induced dipole interaction. So in this actually in the society of these Van der Waals correction methods, we used to tell this London dispersion interaction as a broad concept of Van der Waals interaction. So from now on, I will call this as just Van der Waals interaction. So this Van der Waals interaction arises from instantaneous gel point motion of electrons. So basically, these molecules do not have permanent dipoles, but the quantum fluctuation of electrons can arise some kind of induced dipole they can make molecules have some kind of induced dipole interaction. So it can be called as a purely quantum mechanical phenomenon. So to describe this Van der Waals interaction in a very simple model, there's a kind of a 0-point plasma model which describes these dipole molecules as a pair of quantum harmonic oscillators, which is from the physical chemistry in undergraduate courses. So we can calculate their first acting on the molecule one by the first acting on the molecule one at its resting state, as well as in addition to the first acted by the molecule two based on the dipole-dipole interaction. So the sum of these the sum of these forces can give us the information of force matrix. So we can solve this matrix to get the vibration frequency, which can be written as in terms of zero point frequency, as well as in terms of distance of these two dipoles. So based on this frequency, we can calculate the 0 point plasmon energy, which is simply 1/2 times h bar times 0 point frequencies, and this behaves like one of our R to 6 potential, which is very well known attraction potential in London dispersion, Lennard-Jones potential. So we know that this types of van der Waals interaction arises from the 1/r R to 6 potential, which corresponds to long range correlation, and this is in contrast. Contrasting behavior with the short range Pauli electron repulsion, which behaves like exponentially decaying function. So we need to accurately describe this van der Waals interaction. We need to accurately describe this long range type correlation in theoretical models. However, doing lots of in the previous studies, we're doing lots of material simulation. We used to employ the density functional theory because of its very efficient computational cost, as well as reasonable accuracy to describe material interfaces. But the density functional theory lacks the long range correlation. This is very critical problem because the density functional theory, when it solves this exchange correlation energy, it assumes the semi-local density approximations, which misses the information of the long range correlation between the electron density at long distances. So this semi-local approximations made for the solving the exchange correlation energy makes this density functional theory poor prediction for the van der Waals correction energy, as well as the long range correlation. So the main problem for DFT is DFT excludes these types of long range correlation, and because of this, it fails to describe the van der Waals interaction. So we need to add the correct extent of long range correlation to DFT to make accurate prediction for the van der Waals interaction. For example, in the case of molecular crystals, the DFT, a kind of DFT, PBE cannot predict the crystallization of the benzene molecules, while the aside from the molecular crystals, the graphite also cannot be predicted as cohesive behavior based on the density functional theory, while the reference energy has the interlayer cohesion between the graphene layers. So we need to describe these systems accurately. We need to put the long range correlation in DFT. So beyond the DFT theories, there are many theories to improve the prediction for the van der Waals interaction energies. For example, very high level wave function based methods such as configuration interaction or coupled cluster can predict the correct amount of correlation energies. So it can give accurate information of long range correlation as well as van der Waals interaction, but their computational cost prevents us from applying these methods to very complicated material simulations. And also symmetry of adaptive perturbation theory is also only feasible for small molecules. And for some periodic systems like solids, these days, random phase approximation is available for some plane wave-based codes like VASIP. So this random phase approximation, RPA, enables us to calculate the ACFDT correlation energy, which is fully interacting many-body correlation energy based on DFT. So random phase of RPA gives very correct behavior for graphite binding energies, but its computational cost is still unsolved for many systems. So it is only feasible for very simple solid systems. And furthermore, these days, non-local van der Waals density functional is receiving attention for many studies. So it solves computational cost to the reasonable amount of cost, such as scan RVB10s, but they are basically based on the pairwise additive concept, and furthermore they are a little bit unstable for some systems based on practical applications. So the theory, the simplest but the most efficient theory I'd like to tell you today is atomized theory, which gives reasonable computational cost and reasonable accuracy to predict the van der Waals interaction in material simulations. Also, it includes kind of non-additive van der Waals interactions as well, which I will tell you soon. So atomized theory is basically adding the atomized theory basically adds the van der Waals correction energy to DFT. So it captures the van der Waals correction energy after the completion of DFT energy calculation. So the calculating van der Waals correction energy is very just amount of a few minutes or a few minutes. So it is very fast prediction for the van der Waals interaction energy. And atomized theory has been developed for some diverse groups based on diverse philosophies. So the first one and the most classical one is pairwise method concept. So this pairwise method is basically based on the 1/R6 potential from attraction factor of Lennard-Jones potential. So because this potential diverges as R goes to 0, so they just put some kind of damping function to prevent this kind of diverging behavior as the atoms approaches each other. So this type of potential is these types of potential is summed in a pairwise way to get the total van der Waals interaction energy. So it is very simple model and very fast for computation. And to reflect the chemical environment where the molecules are existing, they calculate the effective C6 coefficient, which determines the strength of van der Waals interaction energy based on the ratio of the Hershey-Field partition to volume between the free atom electronic volume and the effective atomic volume based on the DFT atomic density. So these types of scaling of the dispersion coefficient to C6 reflects a little amount of chemical environment. So we can call it as types of type A non-additivity, which is not a simple pairwise sum, but it reflects a little amount of the chemical environment based on the atomic volume scaling. So these kinds of pairwise methods is very successful in molecular pairs, which are very simple models, such as TS or D3 methods, as well as TS plus SCS, TSHI methods, in comparison with conventional DFT, PBE methods. But the problem is when it comes to the condensed matter, like solid systems. So from molecular pairs to molecular crystals, the pairwise method, such as TS method, increases the mean absolute error for predicting the thermodynamics of molecular crystals about 20 times than the molecular pairs. Not only these kind of molecular crystals, they also predict poor estimation of interlayer binding energy of layered materials such as TS and TSHI methods. So they are helpful to predicting these kinds of interlayer binding behavior for from the conventional DFT PBE energies. So the reason why these types of pairwise methods fails in this condensed manner is that they lack the many-body interactions, but they only just based on the pairwise sum of the potential energies. So what is the many-body interaction? So many-body interaction screens the electron, the van der Waals interaction between two-body interaction by adding the third body of interacting species. So this kind of electrostatic screening by many-body interaction can be called as type B non-additivity, which is really meaning as non-additive potential for the van der Waals interaction. So to estimate the amount of this third body interaction, we can assume these interacting species as fluctuating dipoles or kind of harmonic oscillators, whose Hamiltonian matrix Hamiltonian can be constructed based on these harmonic oscillator models. So this Hamiltonian is called as coupled fluctuating dipole model. So this CFDM Hamiltonian can give us some interacting energy of these three body van der Waals interactions. So including this many-body interaction, they somewhat improve the accuracy for the condensed matters, such as molecular solids or layered systems, but unfortunately they fail for these types of metallic systems where the PB plus MBD method, which is one of the many-body dispersion methods, predicts a very large cohesive energy for the lithium BCC structure. As aside from this many-body method, the previous pairwise method also shows very strong cohesive energy than experimental energy as well. And D3 method shows very unphysical double deaths when its volume is increasing. So these kinds of unphysical behaviors of the conventional van der Waals correction methods give us the question that how we can develop a correct van der Waals correction methods for not only molecules but also metals to describe the interfaces between these two different types of systems. So to describe the correct interaction energy between the molecules and metal systems, we need to think about three types of interactions, which are intermolecular van der Waals interaction energy, which is classically classified as van der Waals interaction energy in organic molecules, and also the van der Waals interaction energy between the metallic surfaces and organic molecules, as well as van der Waals interaction energy that can exist in metallic surfaces as well. So this van der Waals interaction energy can stem from very diverse types of systems, but we usually simulate these types of systems with just one single method. So we need to develop a single standard total energy method for these systems. So to reveal the reason why the classical MBD method fails, we studied the potential model that employs the MBD method employs, and the MBD method is basically based on the point dipole model, which behaves like 1/r potential. And based on the dipole-dipole interaction, it can be calculated as 1/r6 potential, which is like the Lennard-Jones attraction potential. But in these types of metallic systems, metal has very diffuse charge density, so we need to replace this point charge model to a smeared out dipole model with from the Gaussian type charges, because the finite width of the charges can start its charge density overlap from the mid ranges. So we replace the dipole types for the potential model and reproduce the damping behavior naturally occurring from the mid range. So replacing this potential model, we try to reproduce the volume energy curve for the metallic systems. So basically the working algorithm for the van der Waals question method is simply calculate the atom polarizability reflecting the chemical environment, and then compute the full interaction energy based on the smeared out dipole model. Smeared out dipole model. So after then we developed the UMBD method, which is the new type of van der Waals question method, and reproduced very good volume energy curve for the metallic systems, and also diverse types of interacting systems from the molecular crystals to ionic systems and metallic systems. And also some diverse types of layered materials like semi-metallic and semiconducting and insulating systems, as well as the dispersion behavior of the graphite systems as well. So finally, we try to reproduce the real chemical reaction energies, such as intercalating reaction in the lithium-ion battery, where the metal interaction, van der Waals interaction, and ionic interaction are important. So these diverse types of interaction is very important. So UMBD question methods gives very good agreement with the experimental values for these different types of systems, but previous methods fails in some of the systems. So based on this universal accuracy, UMBD method shows very good agreement with experimental values in respect to the intercalation potentials as well. Yeah, so I'm sorry for the delay. So to conclude my talk, we replaced the dipole potential model from the previous model by using the smeared out dipole model, which can reflect the diffuse charge density in the metal systems, and it gives good agreement for the metal systems as well as other molecular and ion systems as well. So thank you for the attention, and thank you for collaborators.
Thank you. Questions? John?
Oh, that was very nice. One thing about MBD that you didn't mention, or I didn't hear you mention, is that it truncates the interaction tensor at dipole terms in the short-range screening part of the calculation. So I'm wondering, as an alternative to doing the smeared out dipole interaction, do you think it would be equivalent to simply treat the higher order interaction terms so that you're effectively including, say, dipole quadrupole dispersion and quadrupole dispersion?
Yes. So actually, we do not include in this model. Of course, we have not included the quadruple interactions or high order. So
what I understand is
yes.
this is basically
Yes.
Pacheco's
Yes.
MBD model, but
Yes.
with a Gaussian blurring on the
yes,
dipole,
right.
So
yes, right.
So what if instead you included higher order terms in the short range screening tensor?
Short range screening tensor. Maybe it can be improved to some extent, but in this model we for the short range screening we use kind of the self-constant screening model. It is also developed by the Tachenko's group. So we just use the range separation scheme for short range screening as well as long range screening. But maybe I can try to think about to further development. So.
Okay, thanks.
Yes. I have a practical question.
Oh yes.
So, for example, if you use crystal package,
yes.
you are using normal basis sets.
Yes.
If you are using WASP, you are using plane waves.
Yes. Right.
Does the code work for both?
Yes, I did actually. I haven't tried, but I think so because the only thing we need to do this calculation is the information about the partitioning. So if the package can do some kind of partitioning like Hirschfeld partitioning or whatever, then I think we can do the calculation for the crystal program as well.
Yeah.
Yes.
Can this you use a PBE, but
yes.
is that also working with others?
Actually, we are also developing the UMBD methods for hybrid DFT function as well to predict both van der Waals interaction energy and band gap as well. So, therefore, we need to fit the UMBD parameters to HSE electron densities as well. So, we are still working on it. Yes.
I cannot see any more questions, so let us thank the speaker again and all the speakers in this session.